First of all, just introduction to myself. I'm very sensitive today. I'm the Chief Technology Officer, Nova Pangaea. I'm a Fellow of the Royal Society of Chemistry in the UK. I did my PhD in sugar chemistry at the University of Oxford. And for the last 26 years, I've been doing process development and scale up with major global companies such as ICI, Croda Chemicals, and more recently in smaller scale-up companies such as Applied Graphene Materials, and for the last 2 years at Nova Pangaea. We are currently based on the Wilton International site, which is the old ICI manufacturing site in the northeast of England in Redcar. So, just an introduction to the process. This has been under development for, well, since the 1960s. It started out looking at processing wood in the State Institute of Latvia. And then through the 1970s and 1980s, went through multiple changes of reactor design. And then finishing up in 2016 when Nova Pangaea got involved for developing a new pilot plant, which is still exists in Latvia, working on a screw reactor. And then that 3 years later continued on to the building of a full-scale demonstration plant at Wilton in the UK. Just to pick up, we're all aware of the climate issues that are going on at the moment, but just to pick up, there's a lot of work on reducing people's carbon emissions, but there is actually only 4 processes which are considered to be net negative. Obviously, direct air capture is one of them. One of the issues there, though, is how do you guarantee that the CO2 isn't leak from your underground storage? There's a accelerated mineralization, so this is where rocks absorb CO2 and become carbonate. Again, a very slow process. A little bit similar to the direct air capture is capturing the CO2 from flue gases. Here, the big problem with this is the amount of water that's required. And then the 4th process is actually the production of biocarbons from CO2 that has been fixed in plant matter, and then through pyrolysis becomes fixed carbon that can then be put back into the ground. So the RefNova process, what's been developed over the last 40 odd years, is to take a biomass residue, and we've worked on wood residues, agricultural residues, so including wheat straw and bagasse. We have a pre-treatment unit which basically reduces the particle size down to about 1 millimeter. And we also do a very dilute acid treatment, and that's to neutralize the alkali earth metals present in the biomass. That material is then dewatered and dried. And then this goes on to our proprietary piece of equipment, which is a steam-assisted pyrolysis unit. This is a linear reactor. And the critical bit here is to mix the biomass with superheated steam. We operate above around about 500 degrees. And basically this decomposes the cellulose and the hemicellulose down to the sugars. And because of the design of the reactor, those sugars are removed from the heated zone as fast as possible. The lignin part of the biomass actually then becomes charred, and that then is then removed from the base of the reactor. So we actually are quite unique that we have 2 product streams. So we have the sugar stream and we have the biocarbon stream. The sugar stream standard process can then go through to fermentation onto ethanol is the main market, and then that ethanol can either be used as a drop-in biofuel or further advanced onto sustainable aviation fuels. The Novachar, the biocarbons, as we've heard, there's all sorts of usage for biocarbon. We're particularly looking at the moment as a replacement for coke into the steel industry so that we decarbonize the steel production around the world. In terms of our greenhouse gas analysis, the first column shows you our greenhouse gas emissions based on the RED II European directive, where the biocarbon is only taken as calorific value as you do the assessment. But already here, we've got quite a large reduction in the emissions comparative to corn ethanol and comparative to the fossil-based line. If you then do an extended assessment where the biocarbon is sequestrated, you can see there's a very large credit for sequestrating that biocarbon back into the ground. So this means that we have a process that overall from the biomass collection through to the factory gate of ethanol, we have overall a carbon negative process. You can see on the right-hand side a picture of our biochar as it comes out of the reactor. This is just a show about how our process fits within the whole biorefinery landscape. So here in the conversion mode, we have Ref Nova. As I say, we have processed forestry residues, woody residues. We have also processed agricultural residues, and we've also processed fermentation residues. So these are residues that can be from a first generation ethanol plants. Our process produces two products, as I said, C5, C6 sugars, depending on what the composition of the feedstock is. Currently, we're operating on softwood, where you have mainly just C6 sugars. There's very little C5 present. Those sugars go through fermentation to ethanol. Ethanol can be then dropped in as a fuel, or through further processing can be converted to jet fuel. But the other process, again, makes the process unique is this production of the biocarbons. So just comparing that then to other technologies, gasification, which is a key interest at the moment in bioprocessing, that basically produces syngas, high temperatures. There then has to be a significant amount of cleanup required of that syngas before it can go through the Fischer-Tropsch process. Our process actually produces the sugars very clean and can go through fermentation without very much cleanup. Other processes to get lignin cellulosic sugars are focused on aerobic fermentation, where they're using enzymes and microbes to break down the cellulosic sugar before normal fermentation. Again, the Ref Nova process, we don't use any enzymes until we get to the, well, there's no enzymes at all, and then it just goes through normal anaerobic fermentation, such as same as first generation. And then compared to traditional pyrolysis, because of our ability to use steam as the carrier, we actually remove those sugars before they decompose down to the oils. And also we get a lot better production of the solid biochar as a second value stream. So talking of the biochar, this is an electron micrograph of the material, and because of the rapid heating that we use, the structure of the biochar stays intact. This gives us a reasonable surface area. This material was about 100 square meters per gram. With a little bit of extra thermal treatment, we can push that up to about 1,000 square meters per gram. So that's equivalent to activated carbon that you get from the fossil fuel process. In terms of the biochar, it produces a very nice high calorific value. Again, this could be used for burning, for cooking, but the material, because of our process, has a very high carbon content. We're up at over 80% carbon. And also because we're using Sitka spruce currently, the ash content is extremely low. And this makes it very attractive as a drop-in fuel for the steel industry. So this process is at a pre-commercial stage at the moment. The picture on the right-hand side is our demonstration plant at Wilton, but we have just started a feed study to scale out this process to a commercial operation, and that's going to become operational in 2023. So basically, we're going to move and add to the current equipment. All these modules then will be connected together to allow the process to run continuously overall. And we will add a fermentation unit. So this first step will give us 5,000 tons of sugar per year, and that will be then converted to 3 million litres of ethanol. The following year, we intend to expand that operation, which will then produce us 10,000 tons of biocarbon and 6 million litres of ethanol, and that should become operational in 2024. Second project we have going on at the moment is Project Speedbird. This is funded by the Department of Transport in the UK. We are partnered with British Airways, or IAG, and LanzaJet. And the intention here is to produce 113 million litres of sustainable aviation fuel. And the intention is to actually build multiple REF Nova plants located at the feedstock, and then transport either the sugars or the alcohol to the alcohol to jet plant. And then that will then be produced into jet fuel and blended into the normal jet fuel. That's about 50%. The aim is to get these plants operational by 2025. That will be producing, as I say, 113 million litres of SAF, but it will also produce 3,000 tons of biocarbon per year. And then in summary, this technology is ready to commercialize, produces 2 valuable product streams from the lignin cellulosic feedstock. It's a modular design, so we are looking to do a spoke and hub model to reduce the cost of transporting the biomass, so we can pre-process it and dry it. The sequestration of that biocarbon gives us an overall carbon negative process, and the fuel grade ethanol we produce gives us the opportunity not just to drop into existing ethanol fuels, but also then to continue and produce sustainable aviation fuel and decarbonize the aviation industry. And finally, that's, as I say, it's a technology ready to commercialize, and that our first units will be operational in 2023. And thank you very much for listening. Any questions?
Yeah, what's the final output now?